Okay, in this lecture we're going to start our section 3.5 material, where we will start considering non-homogeneous equations. And we'll talk about one method for solving non-homogeneous equations, known as the method of undetermined coefficients. So let's start this section by posing the question that we're going to be looking at. Let us consider a second-order non-homogeneous linear differential equation of the form y double prime plus p of t y prime plus q of t y equals g of t, where p, q, and g are continuous functions on some open interval I, so that a solution is guaranteed to exist. So a little review of our terminology here. We say that a second-order linear equation is non-homogeneous if this right-hand side, this g of t function, is anything other than 0. So far, we've been working with homogeneous equations where that g of t function is 0. So if we consider the related equation in which g of t is equal to 0, so if we take the same equation but force the right-hand side to be equal to 0, we refer to that as the corresponding homogeneous equation. So in the next few sections, we're going to see how to solve non-homogeneous equations. And our method for finding the solution of a non-homogeneous equation requires a little background theory, an explanation of why this works. So let's look at the following theorem. This is Theorem 3.5.1 from your text, which says the following. If y1 and y2, capital Y1 and y2, are two solutions of the non-homogeneous equation, then their difference, capital Y1 minus y2, is a solution of the corresponding homogeneous equation. So that is the difference of two solutions of the non-homogeneous equation would solve the corresponding homogeneous equation. And additionally, if little y1 and y2 are a fundamental set of solutions of the homogeneous equation, then the difference of capital Y1 and Y2 would be some C1 times Y1 plus C2 Y2, where C1 and C2 are some particular constants. So let's look at the proof of this result. We're trying to prove that the difference of two solutions of the non-homogeneous equation solves the homogeneous equation. So let us denote, maybe I'll call it capital Y. We'll denote the difference in capital Y1 and Y2. And I want to show that this function now satisfies my homogeneous equation. So to do that, I could find my first and second derivative of this function. So differentiating y, we would have y1 prime minus y2 prime. And then my second derivative, y double prime, would be y1 double prime minus y2 double prime. And so if I substitute these expressions into my differential equation, let's see what we have. So we're looking for y double prime plus p of t times y prime plus q of t times y. And I want to show that this expression will be 0 to show that I get a solution of the homogeneous equation. So let's substitute these expressions that we just found in. Our second derivative would be y1 double prime minus y2 double prime plus p of t times my first derivative would be y1 prime minus y2 prime, and then plus q of t times y, which was the difference y1 minus y2. So if I now group these terms together, if I expand and group like terms, let's see what we get. So I'm going to group everything that involves y1, or one of the derivatives of y1 together, and let's see what I have. Grouping those, I would have a y1 double prime plus p of t times y1 prime plus q of t times y1. And then if I group all of my terms involving y2, or one of the derivatives of y2, well, I see that all of these terms have a factor of -1 that I could factor out. And I would be left with y2 double prime plus p of t times y2 prime plus q of t times y2. And now each of these expressions in brackets is equal to g of t. Why is that? Well, let's look at these expressions. These two equations are exactly the differential equation that I'm considering with capital Y1 or capital Y2 substituted in. But we know that capital Y1 and Y2 are solutions of the non-homogeneous equation. Both of those expressions are equal to this g of t function. So I'm left with g of t minus g of t, which is, of course, 0. So I have shown that capital Y satisfies the corresponding homogeneous equation. Let's state that result. Capital Y, which was the difference of y1 and y2, satisfies the homogeneous equation, which is what we wanted to show. And so the last part of this theorem, of course, follows immediately. It says if little y1 and y2 were a fundamental set of solutions of the homogeneous equation, then the difference in y1, y2 would be some linear combination of little y1 and y2. And that follows immediately because we've just shown that the difference, capital Y, satisfies the homogeneous equation. And if lowercase y1 and y2 are a fundamental set of solutions, that means every solution can be written as a linear combination of those two. So the difference of capital Y1 and Y2 must be some linear combination of little y1 and y2. So now that we have this result, let's look at one other theorem that will tell us how to construct the general solution of a non-homogeneous equation. This is Theorem 3.5.2 from your text, which says the following: the general solution of the non-homogeneous equation can be written in the form y of t is equal to c1 y1 plus c2 y2. So here we have c1 y1 plus c2 y2, where y1 and y2 are a fundamental set of solutions of the corresponding homogeneous equation. And c1 and c2 are arbitrary constants. And then we add some capital Y of t function, where capital Y is some particular solution of the non-homogeneous equation. So let's take a look at the proof of this. We're trying to show that a function of this form is the general solution of our non-homogeneous equation. That is, every solution is of that form. So to prove this, let's suppose that little y of t could be any solution, I'll stress any, of the non-homogeneous equation and let's denote as capital Y, as it is in the theorem statement. This will denote some particular solution of the non-homogeneous equation. Then we know by the theorem that we just looked at, by theorem 3.5.1, the difference of these two solutions, y of t minus capital Y of t, solves the corresponding homogeneous equation. So if little y1 and little y2 are a fundamental set of solutions for the homogeneous equation, then this difference, little y of t minus capital Y, which is a solution of the homogeneous equation, can be written as some linear combination of little y1 and little y2. And so y of t, if I add capital Y to both sides, would be c1y1 plus c2y2 plus capital Y of t. And since lowercase y was any solution of our non-homogeneous equation, well, we've just shown that any solution can be written as some linear combination of little y1 and y2, which formed a fundamental set of solutions for the homogeneous equation, and some capital Y of t, which is one particular solution of our non-homogeneous equation. So this theorem tells us how to construct general solutions for non-homogeneous equations. It says, first, find a fundamental set of solutions for the corresponding homogeneous equation, and then just find one particular solution of the non-homogeneous equation and sum them. And that gives us every possible solution for our non-homogeneous equation. So the method that we're going to discuss first for solving non-homogeneous equations is called the method of undetermined coefficients. And let's describe this method briefly here before we look at some examples. We'll say to find the general solution of the non-homogeneous equation, our first step, step 1, is to find the general solution, c1y1 plus c2y2, of the corresponding homogeneous equation. So to solve a non-homogeneous equation, we will first solve the corresponding homogeneous equation, which we know how to do using the techniques from earlier in chapter 3. And this solution is frequently called the homogeneous solution, or sometimes complementary solution. and it's denoted by either y sub h of t for homogeneous solution, or y sub c of t for complementary solution. And then our second step in this method is to find some solution, capital Y of t, of the non-homogeneous equation. So how do we find one of these solutions? Well, to find this particular solution that we're after, we're going to first make an initial assumption about the form of our particular solution. So this one particular solution that we find for our non-homogeneous equation is called a particular solution and is denoted by either y sub p of t or capital Y of t. Now, when we talk about this method of undetermined coefficients, to find that one particular solution, we have to make some assumption about the form of that particular solution, which we'll see how to do with some examples. And then, according to our new theorem, Theorem 3.5.2, the last step would be to get the general solution by taking the sum of our homogeneous solution and our particular solution.